So in this problem, we have an infinite charged cylinder. I'm just going to draw some arrows on it to indicate that it is infinite. And it has a radius of large r, and we have a constant volume charge density rho. And we're given that the electric field at this little r, which is an arbitrary point outside of the cylinder, is equal to E, or the magnitude of it is. And we want to find rho, the volume charge density. So to do this, we're going to use Gauss's law. The equation for Gauss's law is the electric flux equals the surface integral of E dot dA, which is also going to equal the charge enclosed over epsilon naught. So here, the way we're going to apply this is first create a Gaussian surface. And just because of symmetry reasons, because this is already a cylinder, using a second larger cylinder would be the easiest Gaussian surface. So we're just going to draw a cylinder of radius little r around this smaller cylinder of radius big R. So this cylinder, unlike the charged cylinder, is going to be a finite cylinder. It's going to have a specific height, which we're going to call h. That's the main difference. So now let's just plug in values into this equation. So first we want E. And E is obviously just E. We're already given the magnitude of the electric field. So that's easy. E dot dA. So the area vector is actually going to be pointing in the same direction as the electric field when we're out here. So we can disregard the dot product and just multiply the two numbers normally. So the integral of dA is just going to be the area of this right here. And the surface area of a cylinder, right, is 2 pi r squared for the two circles on the top and the bottom, plus 2 pi rh for the cylinder part around it. But do we really need this whole equation? Because here, when we take any arbitrary dA, right, we have a area vector pointing right here, and we have the electric field, which always points out from the surface. It's going to point like this. And the angle between these vectors, as you can see, is 90 degrees. And when we do a dot product with two things that are 90 degrees away from each other, then we're going to get 0, right? Because cosine of 90 degrees is 0. So we can completely disregard these two circles because there's going to be no flux through those surfaces. So we can just use the 2 pi rh for our area. So we're going to do E times 2 pi rh. So now we have our left-hand side of this equation, we need our right. So now we need Q enclosed, and it has to have something to do with rho because we're trying to find rho. So what is the equation for volume charge density? Your rho is going to equal your total Q, your charge, over your volume. That's what volume charge density is. So our Q is going to equal rho times the volume. And the volume of this little segment of this infinite cylinder that is inside our Gaussian surface is going to equal rho times pi r squared h. Wonderful. So just to clarify something, this is actually going to be large r because we're talking about the actual charged surface that's inside our Gaussian surface. So now we have an expression for Q. So we can plug that in here and say Q is going to be rho times pi r squared h. Great. Over epsilon naught is just epsilon naught. And now we take this and we do some algebra to solve for rho. So rho is going to equal E times 2 pi little r h over, well, times epsilon naught over pi large R squared h. And our two h's cancel out, which is nice because h is not a variable we were given, we just made that up. It should cancel out. And our pi's cancel out, and we get rho to equal 2 er epsilon naught over big R squared.